Morning, everyone. I hope everybody's fine and safe. Just type something in the message room so I'll know that you can hear me and we can begin. Today we're going to have some fun with modeling, and we're going to go all the way by modeling a reinforced concrete beam, simply supported reinforced concrete beam that you can see in front of you. And the reinforcement ratio is provided, and the detailing geometry. I want you just to choose the material, and then we're going to see also modeling of a framing system with 4 columns, drop beams, and shear walls. I'm going to have some fun there and learn a lot of things in relation to how reinforcement affects the mechanical behavior of structural members through, of course, computer methods, which is our finite element analysis software here. Reconan FEA will be used in order to perform all the analysis, nonlinear analysis. The software has the ability to take into consideration cracking through the Schmier-Krag approach. So today we are going to see cracks opening in front of our eyes and crack patterns forming based on the analysis. So we're going to use the 3D detailed modeling approach, which is stated here, which foresees the use of hexahedral elements. We are going to use hexas 8-noded to discretize the concrete domain. And of course, we're going to use rod or truss, as we've seen, or bar elements, and the beam as well, in order to model the reinforcement as embedded rebar. So the reinforcement here is going to be modeled as embedded rebars, embedded rebar elements. Okay, so we will have a mesh inside a mesh. So Greg, we are going to see the engineer, soccer player, and Formula 1 driver joke later. You can share it with us after we are done. Okay, I hope it's not. I hope you have the good joke, because we need a laugh. Okay, so you choose. What do you want? As you can see, we have 4.5 meters long beam, right? And it's simply supported, and force F in the middle. 200 by 450 milli is the section, as it's stated here. I assume a concrete cover 35 milli, 12 millimeters of rebars at the top, and 12 milli in diameter at the bottom, 8 milli every 100 milli spacing for my stirrups. So I have pretty much everything, right? So what I want is for you, based on your knowledge, give me first of all the yielding stress of our rebars. Stirrups and longitudinal reinforcement will assume the same yielding stress. All right, 45. Anyone? 45. All right, 45, for sure, no problem. What about the yielding stress? 450. Okay. And what about the Young modulus for steel? I will assume 200, right? And the concrete? 45 megapascal uniaxial compressive strength, 30. All right, makes sense. So what about the maximum force that I have to apply in order to make this beam fail? Approximately, again, or you can use the exact formula. Again, like we said yesterday, MU is force multiplied by Z, and of course Z, the lever arm, will be equal to approximately 0.95 D, which in this case 0.95. The height here is 450. Subtract the FF 35 milli. Anyone with the calculator? I want you to participate with your calculators, so we can do this fast, because I'm going to develop and show you how to develop the model from scratch. And therefore we'll need some time there. I want at least 2 to verify that this is the correct answer. I want 2 with calculators to type, and not only Gregory. All right, Greg, is this correct? All right, we agree. So this is our Z. Our F in this case will be equal to what? The area of steel multiplied by Fy. I'm going to calculate the characteristic one and not the factor one, right? Given the fact that our software will use the actual characteristic values. So my characteristic values for yielding is 450, and I will not divide divided by 1.15, which is safety factor for my material for steel, right? So in this case here, we'll get that this is equal to 2 rebars in the tensile region, which should be here in the middle, multiplied by B12 squared divided by 4. And of course, this should be multiplied by 450 Newton per millimeter square. So the result will be Newton. So if I divide that over 1,000, I will convert it into kilonewton, right? So what is PI, Gregory? SI, right? Not any other units. So we are using millimeters, newtons. So I want the results in Newton. All right, 101.788 kilonewton. Is this correct? Anybody that wants to dispute this? Yes, Greg and Gregory. All right, great. Excellent. So here we have that our ultimate internal bending moment to reach the yielding stress. By the way, we will assume that the hardening of my steel will be equal to 0. So if this is stress and this is strain, I will assume that this is going to be the Young modulus of elasticity of my steel. And of course, when I reach the Y, the yielding stress, then my hardening modulus will be equal to 0. So this means complete loss of stiffness when it comes to my rebars. So this is going to be 101.788 multiplied by, I will convert the Z into meters as well. So anyone? .1297. So let's say 13 kilonewton meters. All right. And I know that my M external due to a concentrated force in the middle will be equal to PL over 4. Gregory says, correct. And external should be equal to my internal, which is 40.13, and therefore the total applied force should be equal to divided over L, which is 4.5, right? Therefore, P should be equal to what? In kilonewton, 35.67 kilonewton. So for this load, I should get a failure mechanism. Because why failure? Because at this point my reinforcement will reach the yielding stress and my E will be 0. So I will not have any resistance, any additional resistance. So my force F will remain the same. It won't be able to increase. So I won't be able to have internal balance, right? Have you talked about these things during the reinforced concrete design course? I hope so. Anyone? No? Yes? Maybe? All right, this is our film again. Let's start drawing our nodes. The first thing, of course, we need to create new material. We will call this C45, 30 giga UZ, and of course, this is 45 megapascal, Poisson ratio 0.2. I will not take into consideration the self-weight. Given the fact that I apply a load and my calculations are all based on just a single load P which was applied. And of course I will create my steel, which is 450 megapascal of yielding stress. Okay. And then I will have to develop, first of all, my solid concrete. So in this case, this will be C45, hexa C45 for my concrete. I will need to develop also hexa S450. Why? I will also develop discretize the plates at the supports in order to avoid local failure. And of course, I will have my FEA 12, which is going to be beam. I will choose here to draw a shape, which is going to be a circular bar. And given that I have, in this case, 12 milli, right? The radius is going to be 6 milli. Okay, there it is. Everything is calculated. This is minus 6 milli plus 6 milli. So in this case means I have 12 milli in total. And of course, my FEA 8, which is going to have the same type of circular bar section, but the diameter here is going to be 4 milli. All right, cancel, and I'm done. I see my properties here, and I need to define also some custom smart properties. So for my hexa C45, I will define a hexa property, and this is going to be reinforced concrete. And the type here is going to be 3 modified Kotsovos and Pavlovich. The remaining shear strength after a crack opening. So if I have a crack opening, I will have 5% remaining strength along the side of, along the plane of the crack due to the gravel interlocking and friction, right? So this is taken also into consideration. I will assume here my tensile strength is just 5% of the uniaxial compressive strength. The elastic limit, I will say up to 50% of the concrete strength will behave linearly. Then take into consideration micro cracking in order to take into account the deterioration within the elastic region. So actually it's not going to be elastic, it's going to be non-linear even in the elastic region if we assume that the concrete will behave elastically until the maximum uniaxial compressive strength. All right, here I will use a big number just to make sure that the mesh generation procedure will be performed optimally, and if I have any embedded rebars less than 5 milli in length, the software will discard them automatically, and pretty much that's it. All the rest is done. I'm done with my concrete. Now for my steel, I have a hexa property of steel, and that's it. Apply. This is concrete, this is steel, and of course for my FEA 12 I need to define a reinforcement property. A type of element here for my FEA 12, I will choose a circular NBCFB, the advanced element that I told you. 4 fibers are more than enough. 3 integration points are also more than enough. I will use the bilinear model, which is this model here. Bilinear, so we have E and ET, right? Young modulus of elasticity and hardening modulus, that's it. So going back to my model, and if it's a bilinear, this should be always 1, don't ask me why. Young modulus of elasticity, 200 million kilopascal, Poisson ratio 0.3, hardening modulus 0, yielding stress 450 you said, megapascal, so 450,000. Let's say here that at 10% elongation this will fail, no pretension, right? No pre-stress, and of course this should always be 10. Apply. Same thing for our FEA 8. Okay, type of element here I will use rod element, and no fibers are needed. Bilinear is always should be 1. Young modulus the same as before. Poisson ratio, no hardening, yielding. Okay, and of course our failure point 10%, and this is always 10. I'm done. So let's start drawing here our nodes. So I will create the first, let's go back so we can discuss a bit how I'm going to discretize. I'll say, all right, this is 450. Let's say that this is from there to there is 15 cm in order to have an extra area here to anchor my my reinforcement and so on. But again, the embedded rebars are going to be assumed to have full bond condition with the hexahedral elements. So again, I don't care about the anchorage problems in my model. So if this is 15, this is for 50, let's say that we will use 150 millimeters in order to break and discretize this along the X and Z directions. And for the Y, Y, I will use 2 elements along the Y-axis. So if this is 20, so I will have 10 and 10. So a typical element will look like this. Okay, so this is going to be 100 milli, and this and that is going to be 150 milli. So I will draw the first 8 nodes here, and then I will just create my first element and then copy paste it along the X and along the Y and along the Z, and I will be able to reproduce really fast, in this case, my first element. So this is the first, this is the second, this is third, and this is fourth. And of course, I will also change the color of my nodes just to make sure that you can see them, all of you. Make them really fat as well, but not juicy. Okay, and I will copy the nodes along the Z-axis one time. Global axis Z by 15 cm, right? There it is. Then I have model element. My first element should be a type of solid. There it is. Okay, and of course this is going to be hexa 45. My first node is this, second, third, fourth. You go counterclockwise from the base, and then you come exactly at the top, and then again go counterclockwise and press OK. Of course, it's internationally well known that the color of concrete is gray. So there you go. Then, if this is one element, then I will start copy pasting, mesh copy element. How many times should I copy it along the X-axis, or I will copy that once along the Y first, just to create the first section. Okay, 0.1, and then along the Z 2 times. Okay, 0.15 cm, there it is. So this is my first part. Bravo, Ashley says 30, but Ashley, remember, we have 15 cm left and right beyond the supports, right? So you have to take that into consideration. So 32, correct. All right, so I have one, I need another. $31, excellent. And of course, along the X, positive, at a distance of 0.15. And there you go. This is my beam. I don't like the nodes, they are really thick. So let me change them again to make them look a bit smaller. Okay. Now let me create the steel plates. So I'll show you here a nice trick how we can create the steel plate. So we can copy these 2 elements here, one time, negative Z-axis, okay, and of course then modify, come up a bit, modify, update elements, property ID, 1, 2, hexa steel. All right, modify the color now of this. What would you like the steel plates to look like? What color? Quickly, give me a color. All right, red. I would have chosen red as well. So we think alike, I guess. Modify, move the nodes. Let's say we'll make it 5 centimeters thick steel plates. Are they enough based on now your knowledge on experiments? 5 cm, 50 milli, is it enough? Is it strong enough? Is it going to be strong enough? Anyone? All right, everybody who said yes, Gregory says yes. Okay, I will copy this and move it 4.5 meters to the other side. Okay, let's see if this will cut it. No, it didn't. It's fine. We can fix it. We can perform move by element and of course move it by 15 cm. Now, given the fact that I created different elements, I need to merge the nodes. So tools, check coincident nodes, select all, merge all the elements that are found within a distance of 4.8 times 10 to the minus 4. So as you can see here, 1,160 nodes were merged. And of course, I have 408 nodes, 196 elements. Of course, 4 of them are steel and 192 are concrete. Now the fun part, developing the reinforcement. So I have 35 milli in this case of concrete cover. So let's do this really fast. I will copy this along the Y by 35 milli positive. There is the node there. And then I will move it along the Z axis by again 35. There it is. And then I will copy it by 15. So mesh, copy node, copy one time along the x-axis positive by 15 cm. Now I can't see it, but if I show wireframe, then I will see my node there. Can you see the two nodes? All right. So now I'm able to see the nodes and of course create my beam element. This is going to be, as we said, FE12, node 1 and node 2. Remember the direction vector will say yes, y positive is the direction vector, the one that we used in the Reconan FEA, and that's our element. Now let's modify the color. What do you want this element to be? The FE12. Quickly, give me a color. Blue. Vicky, I thought you were going to say pink. Okay. Okay. So let's see this in 3D. Orientation shape. This comes out with F6, by the way. If you press F6, you get the view options window. Apply. And of course, we don't need this anymore. We don't need this either. And solid. This is our first mesh. Copy element. I will copy this along the y-axis. What's the distance that I need to copy this? Quickly, somebody. If I have 35 milli from the left and 35 milli from the right, total is 200. So this has to move by. Okay, and of course I need to copy paste it from here to there, right? So 30 at the top, 35 at the bottom, a total of 450. 450 minus 70. Okay, let me make sure that this is correct. 450 minus 70, quickly. 380. But here is in meters, right? So 0.38. Whoop, there it is. Let's see now the concrete. Is this cool or what? Okay. I guess it's not cool. Okay. We need to finish it to be cool, right? Okay. So let's see. I will mesh copy this longitudinal. How many times? 1, 2, 3, 4. And you see, it's very easy, right? It's not difficult. Bravo. Vicky says 31 times along the x positive 0.15. Okay. And of course, this is my beam, and this is the longitudinal reinforcement. Now let's go to the cooler part, which is the development of the stirrups. So I will go mesh, copy, node. I'll get this node here and copy it one time along the y negative by 1 centimeter. Why 1 centimeter? Is the radius and the radius, right? The radius of the 12 milli and the radius of the 8 milli. And of course, I will move it by another 10 along the negative z in order to shift it down. Of course, I will copy this to the other side. So mesh, copy node. I will copy this along the y-axis one time to bring it somewhere here. And of course, the distance here is 2 cm less than last time. So it should be larger than last time. So 0.15, if I'm not mistaken. We'll see right now. There it is over there. And of course, I will shift this inside so I can place my embedded rebar within the concrete, right? So model element, after I shift it, 1, 2, this is going to be phi 8. Yeah, and what about the direction, the orientation vector? I will choose x this time, positive x. Okay, okay, there it is. Before I move it, choose a color. Orange. All right, orange it is. There it is. Okay, and now I will move it by 7.5 cm, right? 75 milli. Okay, okay. X 0.075, which is in meters. Where is it? It's there, right? There it is. Now I will copy it from there up here. Mesh, copy element. So mesh, copy element. Okay. Okay, along the Z, positive. Before we went 38, now we need to go 40, right? 0.4. There it is, up there. And of course, model element, again, from there to there, phi 8, and from there to there, phi 8, and modify color element. I'll choose all the elements that have a property 4, which is my phi 8, and convert them to orange color. So as you can see, this is now inside my concrete. I will deactivate my concrete from my view and see my first stirrup. Mesh, copy element. So mesh, copy element, select your stirrup, which is made out of 4 macro elements. 31 times again, every 15 cm along the x positive, and there you have it. Our 3-dimensional mesh. This is our grid, right? And of course, this is within our concrete. So what's next? Apply the load. Okay, excellent. So I will modify the color of the node, which is found in the middle. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I will convert them to yellow. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right. So model, load, nodal. I will call this NL, okay, and I will choose 1, 2, 3. I will apply here minus 20, but let us be more accurate here. Let's say that we will have quarter there, and half there. If my total is 60, then model load nodal, I will apply here 15 negative. And of course, in the middle, negative 30. I will perform my tools, check some forces. Okay, and then here I will see that along the z-axis I have 60 kilonewton. Is this clear? Again, there it is, 60 kilonewton Fz, and all the rest is 0. Then model load nonlinear. In order to define, click on defaults to define my static. Let's say I will apply this through 15 Newton Raphson load increments. I will allow 100 internal iterations until reach convergence. 10 multiplied by 10 to the minus 4 is a work criterion. Every time that you need to update the iterations, just do it, and then okay, and that's it. What else? What's next? Boundary conditions. All right, boundary conditions. We have to apply our constraints at the nodes. Let's say here we will have simply supported SS. Okay, 1, 2, 3 nodes here will be pinned, and 1, 2, 3 nodes here. Oh, I made a mistake. All right, let me first of all check for coincident nodes. We have extra nodes, so we'll match them again. All right, again, model constraint nodal. In order to make sure we'll get all the nodes here, I will use the box. Okay, pinned, and of course from the other side, box. Okay, only the TZ will be restricted. So along the X and along the Y, these will be allowed to move. If I restrict the Y direction, it should not make any difference because I don't have any loads applied that will make this beam deform out of plane, right? Everything is in plane. So before we finish here, let us renumber all our nodes along the x-axis, which is the longest direction size of my specimen here. And of course, renumber all the elements, the same thing, x, okay. And let's export our FEMAP neutral in this folder here. What do you want me to call it? Simply supported RC beam. Yes? I think it's enough, right? I don't think 450 milli, let's say it's my span. Always export by allowing the writing analysis model. We export by in version 9, and we can deactivate or activate the geometric and load constraints. This will not make any difference. So if we press OK, then we can come to our folder here, and we can see the file. Now, before we proceed, small pause. We transfer this to another computer, which is my PC1. Now, before we go, and let's copy paste it first of all, but I would like to introduce you to somebody. I would like to introduce you to Mr. Nuclear Reactor Building in new scale, 70 meters long, 30 meters width, and the height is more than 35 meters. As you can see, this is 2 meters tall beams, and as inside here you can see the area and the pool of the reactor building. So let's remove the roof completely so you can see the model. So this model has 2.7 plus million embedded rebars, 180,000 plus hexahedral elements. Okay, so if I remove the walls, let's say, and the arcs, if you zoom in here, you will see the embedded rebars. Can you see them? So this is one of the largest models that we created so far. And we have a few issues with the memory as well when we upload this model. Okay. All right, now that you've met Mr. Wonderful, let's see here what we have. All right, there it is, our model. Start our software, paste the name, run the analysis. Oh, what happened? $33, load increment 34, so we got the 60 kilonewton. We divided them into 15 Newton-Raphson steps, and we applied them each and every time. Step 1, 2, 3, 4, 5, blah, 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 33, 34. What it says, tension rebar, failure inside hexa 213. All right, let's see, let's allow it to write the output set. By the way, again, what's the required time? 1 second, right? Go try to do that with other software. All right. By the way, we created the model here live in class, which is another plus. So this is Reconan 9. Now we are going to use Reconan 9 to represent the crack opening and the crack pattern propagation as they resulted, the crack patterns for each and every load increment as they resulted from the analysis. So the analysis here, let's move this here. First of all, we're going to show the cracks as squares. You will see some white lines. So the first thing that I will do is to animate the deformation history. So let's see what will happen here. Oh, cracks appeared in the middle. That was it. So let's see again the animation. All right, let me zoom in a bit in the middle and do it again. So what do you notice? Does that make sense? Let's draw the deformed shape at the, let's say, load increment 20. Let's go a bit back, 15. Load increment 17. 16. There it is. The first point where I had the development of cracks. Are these, what type of cracks are these? Ahmed, Heino, Jeremy, people that are not participating usually, give me an answer. What type of cracks are these? Shear or tensile or compressive? Anybody? All right, everybody says tensile. Stefan says tensile. All right. Does that make sense? Do you agree with what the software has computed? Does that make sense, Mugeni? So we have perpendicular cracks, which of course are exactly what we expected. Why? Because we have a bending moment here that causes tension at the bottom and compression at the top, and we know that our cracks are going to be perpendicular to the tensile principal stresses. And of course, the tensile principal stresses will look like that. So this is what the software told us as well. So we do agree. And of course, as we increase the load, crack spread increase, thicken, as you can see. And of course, we have what? The crack at load increment 33. 34 is failure. 33 has managed to resist to the loading, and that's it. And you see the thicker cracks are found in the middle. And the next step, the step 34, our algorithm did not manage to converge due to, what do you think? So let me get the output file, bring it back home. Why did it stop there? Failure mechanism at 35.67 kilonewton, Vicky says. All right, let's see. So this means that we reach the yielding stress, and at that point we reach the maximum, right? Okay, let's import now the results within FEMAP. Anyone else has a different explanation? So let's see. Deform shape at load increment 1, show us the total translation, and show us the von Mises stress. Okay, form and show us the contour. So it tells us that for the first load increment, okay, the first load increment, I have 60 divided by 50 steps, 1.2 kilonewton. The stress that is developed, the maximum is 143.8 kilopascal. Okay, second load increment, by the way, this is not to scale. So if I want to change and show the actual deformation of this beam, it will look like that. Can you see anything? Do you see the deformation here? We have like 40918 meters, which is less than a milli. Now, if I want to say, look, all right, I see you, right? Like in the Avatar movie, I see you. Let's use a scale factor of 1000 and then show this deformation. All right. Now you see we can do whatever we want, right? One might say, well, where is the reinforcement? Well, there is the reinforcement deforming along. Can you see? Okay, so this is step 2, 3, 4, 5, 6, 7, 8, 9. Now let me change the scale to, let's say, 100. 10, 11, 12, 13, 14, 15, 16. Oh, what happened here? It says here 0 stress. All right, Gregory, yielding at the load increment 16. Anybody else? Bravo, Vicky. All right, cracking, excellent. So why, Thoriso, why do we have 0 stress there instead of having larger stress? When the concrete cracks, what happens? We have a discontinuity, right? So the stresses there. Do we have actual stresses within a crack? Anybody else? We have the remaining stresses, right? Or any friction or whatever. But in this case, definitely we don't have anything. So in order for us to be able to visualize the deformation and the damage area development, I will change from stress to strain. So I will see the deformation. And as you can see, load increment 15, everything is like ideal and elastic, but when the crack occurs, strain concentration, and of course, if I continue 16, 17, 18, and so on, 31, 32, 33, bam, 34, I have no data. 33, maximum deformation, 9.49 millimeters. Now say, can I develop the P delta curve? The P delta curve, of course I can. If I take the node of this point here at the base, that is 327, remember that number. I go to XY versus set value, show me the T3 translation, which is the Y translation of 327, and press OK. Then I will see this lovely curve. I will be able to execute here list output XY plot, and I will see here the points of this curve. I will be able to copy them and then start my Excel. My Excel is start. Then come here, Control V to paste. As you can see, nothing, they are not within the cell. So I will go text to column, determined, next, space, finish, and everything now is as it should. Total applied load, 60 kilonewton. 0, this will be equal to my 60 kilonewton, fix the cell, multiply by the percentage of the applied load. This is the percentage. 2%, 4%, 6%, and so on. Copy this till the end. Therefore, we reach there, all right? And this is the deformation in meters negative. So I will say minus 1000 multiplied by this to convert this to millimeters positive. And of course, as you can see, maximum deformation at 9. And then here I'll say, okay, use the 39.6 and this, let's say, make this equal to 15, just to have a horizontal line at the point of failure to make it look nicer. Insert, in this case, the graph. Select data, add X. This is my X here, and this is my Y here. Okay, and there it is. So what did we calculate as maximum load of failure? All right, but we assume that this is 0.95, right? And also we assume that we don't have any compressive reinforcement. So let's say if we assume that this 0.95 is actually 0.98, and we divide this, multiply this by 0.98 and divide by 0.95, then we'll reach even closer to this value here, which is my 39.6 kilonewton. So what do you think? Is this a good an acceptable prediction? Let's say if this was your script, would you have accepted it? Would you have accepted it for your scripts? Again, anybody? Greg says maybe. Okay, that was harsh. Gregory, what would you have accepted then if you don't accept this this prediction? By the way, you compared a numerical result with an analytical result that is as simplistic as it can get. All right, let me ask you something else, Greg. Would you trusted more the formula or this result here? Why the result? Greg says the result. Gregory as well. Why? Gregory says taking into account each finite element. Greg says the formula is too simplified. All right, so definitely the formula is definitely very simplistic. There is no doubt about it. So our model, our finite element analysis model, it takes into consideration different phenomena that the formula doesn't take into account, including the deformation of the section, including the micro cracking, cracks, and so on, phenomena that are not accounted for when we are using the simplistic formula, right? Okay, so what do we have here? We have the total applied load, kilonewton, and here we have in millimeter, right? Millimeters. All right, so what will happen now, and let's do this before we leave for our first break and last one. What will happen if I add hardening to my longitudinal reinforcement? So here I come back, show me the model. By the way, this is the deformed shape of the rebars, as you can see. And if I want to animate this, and I can also animate, think about my question as at the same time as I'm talking. All right, one solid von Mises strain. Okay. This is the animation. And of course, if I want to make it look a bit cooler, I can do the same by animating the concrete. So what will happen if I come back here? I go to my feed 12, and in the schmaz I'll say, all right, use it 1% hardening. 1% hardening, 2 gigapascal. What will happen to my delta curve? Strain hardening will produce additional plastic deformation, and the metal will become stronger and more difficult to deform, Gregory says. So the entire, in this case, mechanical behavior after we reach yielding will be modified, right? So this is when my hardening will be activated, when I reach the point where my hardening is activated, which is the yielding point, right? So let's see here. This is our new, okay. I will run the analysis here, okay. All right, there it is. Oh, what did you notice? All 50 steps are finished successfully. Okay, that's interesting, definitely. And of course, I will just close this and import my new results by, first of all, deleting the old ones. File, import, analysis, output, okay. And then what I'll do, I will drip again my curve. There it is. So list, output, Hipsy plot, get the new curve over here. Okay. Okay, copy, paste this here. Okay, copy this there. All right, and of course take this here. And of course, this is with hardening. And I will add now, let me make this bigger for you. I will select my data. I will add a new series. Okay, this is going to be my X, which is found here. And this is going to be my Y axis, which is here. Okay. 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 And of course, let's change this to 47 just to make the lines equal. There you go. So what do you notice? Definitely my hardening contributes to the development of additional strength, and it's definitely not a correct way to go if we assume that our reinforced concrete structural member will fail at this point, which will not in reality, given the fact that we'll expect either a rupture of the longitudinal reinforcement or a failure of the compressive zone for this case, which is a structural member, a reinforced concrete beam, which is 100% bending moment dominated. All right, let's have a 10 minutes break. And for those that want to chit chat, you know where to find me. Thank you. You can ask me about anything you like, by the way, during the break. So feel free to use this time as well in a constructive manner. We will discuss assignment 3, yes, at the end, definitely. Okay, everybody, let us begin. Just type something in the message area so I can make sure that you can hear me. Are you still with me? All right. Okay, so before we finish today's session, I wanted to show you, in this case, a model that I actually developed for the needs of STU311 theory of structures that I offered to the architects. So I didn't want the architects to be more advanced than we are, so I wanted to show you the same thing. So far, I think we've been doing a good job. So I wanted to investigate the mechanical behavior of this 4-column frame, which has a slab and drop beams. As you can see, we have drop beams in the back area, and here we don't have any drop beams. 20 milli, 18 milli, 12 milli, and 8 milli are used in order to reinforce, in this case, the framing system. So let me see here. I will show the cross sections so we know which is which. So I'll also zoom in here. So as you can see with pink color, I think is the FEA 18, which are 2 FEA 18 up at the top and 2 FEA 18 at the bottom. The 20 milli are used for the columns. So the blue are the 20 millimeters. The green is the 8 milli, this one. which is used for stirrups for the beams and for the longitudinal reinforcement for our slab. And of course, the 12 are the feet 12 is used, the 12 millimeters diameter is used for the stirrups within the columns. As you can see, there is a uniform distributed load, but I will just deactivate it in order to allow us to view the reinforcement in a better way. So do you recognize the reinforcement for our slab? Do you see any reinforcement missing? Anybody? This is the concrete, and within we have the reinforcement. Can anyone comment on the reinforcement of this slab? Is it acceptable? Do you like it? Is something missing here? Gregory, the bars, Gregory says, are the bars tied into the beams? They are embedded within, yes. They reach up to this point, and remember, in the model, we assume full bonding. Okay, so this is full bonded with concrete, so we don't have any issues with slippage. But we can't take it into consideration when we perform cyclic loading. Sorry, so in the middle, he says, what about the middle? Do you have any problems in the middle? If I see it from the top, I have along the X and along the Y my reinforcement. I have here top reinforcement for the negative moment, which will generate tension at the top. I'll give you a hint. There is one reinforcement which is missing in order to make this complete. Which one is it? Have you spoken about edge reinforcement? Edge reinforcement. You have to place edge reinforcement where the slab is, the free edge of the slab, right? Which is a U-shaped reinforcement, and it has to be placed here and there. But that will not contribute to the strength of the slab because this is just for spalling, right? To avoid spalling. Have you ever heard about it? Edge reinforcement? Yes, no? Sounds familiarly. Okay, so if I have let's say a section, and let's say this is a section of my slab, then I have to apply a U-shaped reinforcement here. So this is from this side, of course, and 8 milli every 15 centimeters will do. And of course, the length here should be at least 2h, where h is the thickness of your slab. And don't forget that you have also you will place a rebar there along the direction here, this one. So if this is your slab, you have a U-shaped here and a U-shaped there. Let us assume that this is the top view of my slab, and I perform a section like this. I'm drawing it really fast. Okay. And this is my section, right? And of course, you will have the reinforcement here at the bottom along this direction. And of course, the reinforcement vertically. So you will be looking at dots every X where X is spacing, right? And so on. All right, so this is edge reinforcement. As you can see, we don't have that here. All right, after running the analysis, the vertically applied load was divided into 5 steps. Before we move ahead though with the results, I will not run the analysis now, we'll run another analysis together. So the total height is 3 meters, and this is 4 by 8 meters, and this is 3.6 meters along the Y direction. So the Y is 3.6, and the X size length is 4.8 meters. Okay, the thickness of the slab is 2.823, 18 cm, 180 milli. Okay, the drop here of the beams from there to there. Okay, let me see again, from there to there, 50 cm, so 0.5 meters. And as you can see, the width is the same as the width of the column. So from there to there along the Y, 30. So this is 30 cm, and from there to there X40. So this is 30 cm by 40 cm, the column section. 30 cm width and 50 cm is the height of my drop beam. And of course, 18 cm is my thickness of the slab. Now for 1% plus, where do you expect to have the development of the largest deformation and the first damage development? Let's see how well you know your structures and reinforced concrete behavior in 3D. Now this is what separates civil engineers that do understand mechanical behavior of structures and those that don't. And they use just the formulas blindfolded, right? So here we have an overall understanding, and I expect from you to have an overall understanding on what to expect from a three-dimensional realistic structure. Gregory says, center of the slab. Anybody else? Anybody else that would like to give it a shot? So let's see, file, import, analysis results. These are the analysis results here. So let's see. Now let us show first of all the deformed shape of the first load increment, total translation, von Mises strains, and of course, in order to make sure that we get it right, let's show first of all the deformation. I will deactivate the reinforcement. Okay. And decrease a bit the deformation style. Let's say here, again, I will use 100. Okay. Let's make it a bit bigger. The scale, increase the scale a bit more. All right. Just to be able to visualize the deformation. So what do you notice? Gregory, in addition to that, I will also deactivate the edges just to see it as a real structure. Now that's cool, right? So what do you notice? 4.8 meter span, 3.6 longer span, bending of the beam, even though I don't have, in this case, a drop beam along this direction, right? So due to the fact that this is almost 5 meter span, it's affected more, and the deformation that is developed looks like this. Also here in the corner, here, there, and there, I see the development of deformation due to the asymmetric bending. Have you seen the asymmetric bending? Did you notice the asymmetric bending? If I increase this by 10 times, do you see what the asymmetric bending looks like? Okay, so load increment 2, 3, 4. Oh, what happened? Look at that. What is this here and there? Anybody? Sudden increase of this local strain concentration here and there. Why here and there? Anybody? Cracking, right? Horizon is correct. We have crack development, strain concentration, but why here and there? That is large. What? We reach the maximum tensile or compressive strength. And why did we reach that strength? Because of what? Shear, axial force, bending moment, torsion. Anybody? Max tension due to bending, Stefan says. Absolutely correct. So, due to the fact that we have a sort of a bending about the diagonal axis of the section of this column, we have the development of a crack here. But so far, our professors told us that we have a rectangular section and bending moment, tension is at the bottom and compression is at the top. Now, this is the behavior of a real structure. We don't have bending moment, which is exactly symmetric and applied from at the neutral axis that passes, and it is parallel to the actual lower and upper fiber of my section. This is a myth. This is a simplification. So now you can start understanding what's going on within a real structure and how a real structure will behave. One might argue though, look, the bending moment does behave like what they told us. I'll say yes, no objection. But what about if I apply a horizontal load about this point there and the whole thing develops a rotation about the z-axis, so the whole structure will rotate? Would you like to see that happening? We can't do it, by the way, if we have time. So let's see then load increment 5. So as you can see here, now the slab started to develop also crack at this area here. But again, the behavior is dominated along this direction. Now, what will happen if I increase this direction, the 3.6 direction, and remove the reinforcement from the top area where the connection between the slab and the drop beam occurs? F8, exit, rotate the z-axis. So what I'll do, I will delete more the output, all, okay. I'll come here, okay, bring back the nodes, all the elements, remove the concrete, delete model element. Let's be let's do something crazy. Okay, all right, delete model node. Let's say that the rebars there from there to there are problematic, and they practically have 0 tensile strength. Okay, and okay, I will move the nodes here along the y-axis by 1 meter, and I will move the nodes here along the negative y by another 1 meter. Okay, and I will also modify the area, the applied load, and increase it in order to take into account the increase of the area here. So let's say I will increase this by 1.5 times. Okay, modify, renumber node, select all, let's say X, modify, renumber element, select all, X, file, export, FEMAP neutral. Let's substitute this existing file here, so I will copy the name here, and then yes, replace, and run the analysis. So let's go back to our folder here. This is the one. As you can see, this was created at 12:54. Now it's 12:54. Run the software, paste the name. 1, 2, 3. You see load increment 3 started with nonlinearities, or load increment 4, 5 struggling to converge. Okay, file, import, analysis results. Okay, this is my Reconan FEA, but I will not see the cracks. I will just want to, in this case, represent my results. Okay, so what do you notice? A slab failed in Durban, and 1 person was killed, 3 were injured. Reminds you of something? Anybody? Does that make sense? The results? Now that we removed the longitudinal reinforcement from that area, you see we have plastic hinge development at the slab level, right? The entire slab, in this case, developed a region which is damaged, which resembles to a plastic hinge. If we look at it from this direction, let's remove the deformation. So what we notice here, this area here was damaged. But the out of plane stiffness of this frame here and that frame there definitely helps in order to avoid the failure, and somehow we have the ability to carry the loads, but definitely this is not an acceptable design, right? Definitely. There is no doubt about it. And of course, what will happen if I remove the reinforcement from the top area here? Would you like to see that as well? And of course, like last time, one last thing is view, post, dynamic counting plane. Okay. Okay, choose a plane along the, we'll choose a plane along the YZ. 0, 0, 1, 1, 1, 1. Okay, and I will change this to positive then. There it is. Stress development within the frame as it resulted from the analysis strains, and we see the damages within the volume in 3D. All right. Any questions? Any questions before we start discussing about our assignment 3, which has been already uploaded for you on ClickUp? Okay. Give me a second. All right, I'll do it again. All right, there it is. All right, I'm giving you this structure. It's a truss roof. As you can see, there is a glass finishing at the top. The thickness of the glass is 10 millimeters. And the first and last span, the length of this truss and this truss here, and this half and there is 1000 plus R. This is 500 plus R. So the total in any case should be 5000 plus 2R, which is in millimeters, where R are the 3 last digits in millimeters, of course, of your ID. This column is a hair column, which provides a rigid base for this truss. So the truss is connected here and there. Here means connected to the drop beam, which is reinforced concrete. So as you can see here, the joints can rotate, but it is welded here on this cantilever, which is made out of steel. So this provides a rigid support as well. And this can rotate, but it cannot move. The same thing applies for this connection here, which is given to you. This detail, the connection detail with the hair column is given here as well. So you will treat it as a 2D beam. Is this clear? Do you have any questions related to the geometry? Anybody? All right. So what I want you to do for this realistic structure, right, which is 2D, which is not realistic, but it is realistic if we see it from as a section. Greg, keep the comments to yourself, please. We're not going to solve this now. You are going to solve it one by themselves, so, okay, as individuals. You will make the decision on whether to use pins, fixed supports, or rollers. It's up to you. Idealization of the structure. Okay, Greg, this is clear. Okay. A, draw to scale the mesh including the boundary conditions by using, of course, the two-noded bar finite element. And by boundary conditions, I refer to the constraints and loads. Make sure the numbering of nodes and elements is shown. So I want you to draw the mesh and then number the nodes and provide the numbering of the elements as well. Then I want you to create a table stating the number of nodes, elements, and degrees of freedom of the developed 2D finite element model. Then I want you to provide with a table stating the global degrees of freedom of each node, right? So you will have a table, node 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and whatever. And node 1 has this, node 2 has these global degrees of freedom, right? Then I want you to compute the global stiffness matrix of all finite elements found within the developed finite element mesh. Do not repeat matrices that are the same in terms of geometry so as to minimize the length of your answer. Thus, group the elements. You say element 1, 5, 6, 7, and whatever. This is the stiffness matrix. Elements, this, and that. This is the stiffness matrix, right? So you will have groups, and you'll say these are the elements that have this stiffness matrix, these are the elements that have this stiffness matrix, and so on. I don't want you to take each and every one of these finite elements that you will have eventually in your mesh and write the same matrix over and over again, okay? If you choose to do so, definitely it will not be beneficiary from the point of view of spending ink. Then what you'll do, you will develop the unreduced and the reduced global stiffness matrices of this numerical model. The area is missing here, so I will update the file soon, okay? You will assume an area of 0.01 meters. So the area here, I will add it now after we finish this session, will be 0.01 meters square. Okay, I will update the file, so don't worry about it. This is something that you will need. Okay, any questions about this part before we move to the second part? Anyone? Greg, of course, all by hand. If you choose to draw to scale your model by using AutoCAD, then you can use that one in a snapshot. In any case, everybody will have a different geometry, so you can use AutoCAD or even a finite element analysis software to provide with a snapshot of your model. Is it okay? You can provide the tables as well in a Word format if you like. But the stiffness matrices, I want you to do it by hand, yes. Did I cover you? All right, thank you. Now, second part, I'm giving you this reinforced concrete frame, column AB, beam BC, and column CD. Beam is 250 by 500 milli. It has two rebars of 20 milli at the top and two rebars of 20 milli diameter at the bottom, and 8 milli every 100 milli spacing stirrups. And this is the column, which is a 300 by 300 milli reinforced concrete for a total of 422 milli in diameter longitudinal rebars and 10 milli every 100 milli spacing for stirrups. You can see the geometry where R again are the last three digits of your ID, and all the dimensions here are given in milli. So what I want you to do first, I want you to use Reconan FEA academic version and develop the DAT file of the model of the reinforced concrete frame. These are the assumptions that you will make, and you will assume a nonlinear analysis. This is the load that you will assume the 75 kilonewton horizontal load applied at joint B. And of course, you will apply this through 10 load increments. Neglect the self-weight loads, no other loads, only a horizontal load. Is this clear? Then you will run the analysis and you will draw the delta curve in an Excel and then state the maximum horizontal displacement that you got from this analysis. Is this clear? This you can do in a Word, no need for handwriting. And then I'm asking you, what is the horizontal increase or decrease if the two columns longitudinal reinforcement is increased to 4 feet 22 top and 422 milli down in the bottom? Provide also the new DAT file. Then, if a static vertical load of minus 10 kilonewton, in this case, is applied at B and C respectively, okay, let me see. So if you apply a load here, static load, 10 kilonewton, and there, 10 kilonewton, so 10 and 10, what will happen to the horizontal displacement after you apply the 75 kilonewton? Explain through developing the relevant model, provide again with the new .dat file, right? The input file. And of course, your results. Is this clear? Any questions on this one? Again, you need to idealize this structure. Okay? All right, nobody's saying anything, so I assume that everything is fine. And I'm giving you a bonus question. Ashley says, must we submit the DAT file on the contents of the file? No. The DAT file has a DAT file. that file, give it a name, then the second that file another name, and the third that file another name. So you can use the WinRAR, compress everything, and then upload a single file. Now that I showed you how to use WinRAR as well. Is it clear? Okay, all right, great. So this bonus question foresees the use an FEA software and develop the finite element analysis model of the 3D structure by including the column as well. And of course, you have to apply the dead loads and show me the deformed shape and comment on your results. So this is the top view, and this is the actual side view of your structure. Is this clear? Any questions on the bonus question? All right, I will update this file by adding the area of the section to be 0.01 meters square, just to make sure that everything is included. And I believe that's it for today. I'll see you next week. Thank you for being here. Bye-bye.